In this video, I will talk about the numerical descriptive measures of population. Descriptive statistics discussed previously describe the sample, not the population. Summary measures describing a population, called parameters, are denoted with Greek letters. Important population parameters are the mean, the variance, and the standard deviation. So to calculate the mean is the same way when we calculate it with the sample. You add up all the numbers and divide by the total numbers that you have. In this case, we use mu to denote the population mean. The variance is calculated differently, but not too much. If you look at this formula, you divide by the total number of values. When we did the sample, we divided by n minus 1. Okay? The population variance is denoted by the Greek letter sigma squared. And to figure out the population standard deviation, you just take the square root of your sigma squared. And this is the most commonly used measure of variation. It shows variation about the mean. Once again, it's the square root of the population variance, and it has the same units as the original data. So I'm not going to show you how to calculate this by hand. I will show you how to do it in StatCrunch and in Excel. So if we go to StatCrunch, I already have my data values listed under the example column. So what we'll do is we'll go to Stat, Summary Stats, and Columns. I'm going to click on Example, and we want the mean. Like I said, the population mean is calculated the same way as the sample mean. If you look here, we also have variance and standard deviation. We do not want to click on those because that will calculate for the sample. The ones that we want, if you scroll down, would be unadjusted variance and unadjusted standard deviation. So we want these two. That's for population. And when I hit compute, I get my answer. My mean is 7.5, the variance is 12.85, and the standard deviation is 3.58. Okay. If we go to my template that I have for this chapter, once again you type your data values in column A, and this is the central tendency tab, and the population mean will come up. Like I said, it's the same as the sample mean. So I have it all in one spot, so it's 7.5. To do the variation, once again, you input your data in column A, and under measures of variation, if you look below, I have population, standard deviation, and variance. So it's these two values here. You can take your mouse and click on the value so you can see the command. If you look here, if you look up, it says var.p. That P indicates that you're calculating for a population. But when we did the sample variance, if you click here, you see var.s. So it's a different command. The S is for the sample. So that's the difference between these two. But I did indicate which one is the population, so you'll know how to find it on the worksheet. Okay. So once again, when we deal with population parameters, we deal with Greek letters. When we deal with sample statistics, we just deal with regular alphabet letters. For example, for mean is X bar. For variance, it's the letter S. So now let's talk about the empirical rule. The empirical rule approximates the variation of data in a symmetric mound-shaped distribution. You can expect approximately 68% of your data to be within one standard deviation of the mean. And that's indicated by this picture. If you go out one standard deviation above and below, you should expect 68% of your data values to fall within those two values. You should expect 95% of your data to fall within 2 standard deviations. So if you go 2 standard deviations above and below the mean, you should expect 95% of your data values to fall between those two values. And then for 3 standard deviations of the mean, you should expect 99.7% to fall of your data values to fall within those two values. So suppose that the variable math SAT scores is bell-shaped with a mean of 500 and a standard deviation of 90. So in this problem, they indicate that it's bell-shaped. So it's mound-shaped, or you can say it's symmetric. You would expect 68% of your test takers to score between 410 and 590. Well, how did we get this? Well, they told you that it's 1 standard deviation from the mean. So if you took the mean 500 and subtracted off 90, you'll get the 410. If you take the 500 and you add 90, you'll get the 590. You should expect 95% of all your test takers to score between 320 and 680. Well, how did we get that? Well, 95% is 2 standard deviations. So if you took 500 minus 2 times the standard deviation, 2 times 90 is 180. So if it's 500 minus 180, that would give you the 320. If you go out 2 standard deviations above the mean, it will be 2 times 90, which is 180 again. So you're going to take 500 plus 180, and that's how you get the 680. For 99.7%, that would be 3 standard deviations. So we'll take 500 minus 3 times the 90. This is how you get the 230. And you'll take 500 plus 3 times 90. And this is how you get the 770. Next, we'll talk about the Chebyshev rule. And regardless of how the data are distributed, at least 1 minus 1 over k squared times 100% of the values will fall within k standard deviations of the mean. And this is for k greater than 1. So examples, if you go out 2 standard deviations, according to this rule, you should expect at least 75% of your data values to fall within that range. And if you go out 3 standard deviation, you would expect 88.89% according to Chebyshev's rule. So let's look at an example. Consider a population with math SAT scores, and you determine that the mean is 500 and the standard deviation is 90. According to Chebyshev's rule, what percentage of math scores is expected to be within 8 standard deviations of the mean? So what we're going to do is we're going to use this calculation. So this time they told you that the standard deviation is 8. So I'm going to take 1 minus 1 over 8 squared. Okay? And then in order to change it to a percent, we're going to multiply it by 100. So when you do this, 1 minus 1 over 8 squared is 0.984. And when you multiply it by 100, you'll get 98.4%. So you can expect 98.4% to be within 8 standard deviations based on this rule. So let's go back to this problem again. And according to Chebyshev's rule, at least 87.5% of these scores are expected to be between what two values? So in this case, we are going to solve for k. They told us what the percentage was. So if I take 1 minus 1 over k squared, I'm going to set it equal to 0.875. I'm going to solve for k. So the first thing I'm going to do is I'm going to subtract 1 from both sides. So when I subtract 1 from both sides, I end up with a negative 0.125. I'm trying to solve for k. So the next thing I'll do is I'm going to cross multiply, I end up with negative 0.125 times k squared. To get k squared by itself, I'll divide by 0.125 on both sides. And you should know that a negative over a negative will give you a positive answer. So here you would get 8 is equal to k squared. To get k by itself, I'm going to take the square root of both sides. And I get k is equal to 2.83. So this is the standard deviation. All right. So now to figure out what two values that 87.5% of these scores will be between, what I'll do is I'll take the mean, 500. I'm going to subtract 2.83 times the standard deviation. Okay. I'll also do it with the addition. So let's go ahead and see what we get. I have 500 minus 2.83 times 90. I end up with 245.3. When I take the 500 plus 2.83 times 90, I end up with 754.7. So we can expect 87.5% of our scores to be between 2.453 and 754.7.